Now that we know how to find gradients, we're going to use them to calculate what we call directional derivatives. So let's take a look at this definition and see if we can make some sense of it. The directional derivative of f, and f is going to be our function in the diagram. That's that blue surface that we're looking at. So the directional derivative of f in the direction of the vector u, which is a comma b. That vector u is a two-dimensional vector, and in the diagram it's sitting down there on the ground in the xy plane. So here's this directional vector u, all right? And it says that the directional derivative of f in the direction of u is the partial of f with respect to x times the x component of the vector u, the partial of f with respect to y times the y component of that vector u. Okay, so what in the world is this going to tell us about the function? So what the directional derivative does, it goes to a specific point. So we've got this point down here in the xy plane, and we've got this given unit vector pointing in a certain direction in the xy plane. And it says, okay, I'm going to go up to the surface at that point, and I'm going to see what the function is doing in the direction of the vector u. Okay, so we kind of have a tangent line drawn there. So this directional derivative is actually going to calculate for us how much the z coordinate of this function is changing in the direction of that vector u. Okay, so how does it do that? Well, it starts off with the partial of f with respect to x. All right, so the partial of f with respect to x, remember that that takes y as a constant and looks at how the function is changing in the x direction. All right, so we're going to take y as a constant, and we're just going to look in the x direction. So it's going to go up to the surface and say, what is that surface doing in the x direction? How fast is the z component changing in that direction? Okay, then it's going to look in the y direction. It's going to hold x constant, and it's going to look in the y direction. So it's going to go up to the surface and say, okay, how much is the z component changing in the y direction? Okay, and then it's going to take a kind of weighted average of that. It's going to take a little bit of f sub x and a little bit of f sub y and mush it together. All right, so let's just say that that vector u pointed a bit more in the y direction than it did in the x direction. So this b would be a little bit bigger than a. So when we go do this calculation here, you're going to get a little bit more of f sub y because b is a bigger number than a. Likewise, if a was the bigger number, then you would get a bit more of the partial with respect to x. Okay, so it takes a little bit of the x direction, a little bit of the y direction to get the change in z in the u direction. All right, so we're hopefully going to make more sense of that in the next few slides. But before we do, I want to give you a shortcut for calculating the directional derivative. Okay, so notice in our directional derivative formula, we've got the partials with respect to x and y. Remember that those are the components of that gradient vector, right? So think about the f sub x and the f sub y. Okay, those are just being multiplied component-wise by the components of the vector u, a comma b. So this is like we took a dot product of the gradient vector and that unit vector u, a comma b, right? We would just multiply x components, multiply y components, and add them together. Okay, so this directional derivative is just our newfound gradient vector dotted with this unit vector u that we're given in the problem. All right, so there's a shortcut formula that I just showed you on the last slide. Gradient of f dotted with u gives you this directional derivative. And I want you to think of this directional derivative as a kind of slope. So think back to algebra when we first learned about slope. So let's say that you had a line m equals 2. When you would go to graph that line, you would rewrite that 2 as 2 over 1, right? So you could do the rise over run, all right? Because slope essentially gave you the change in y for every change in x. Right, so we would go 1 unit in the x direction, and then it would tell us how much we had to go to tick marks in this case in the y direction. So this directional derivative is kind of the same thing. It's telling you how far, if you go 1 unit in the u direction, wherever u happens to be pointing, how much would your z coordinate change to get onto that tangent line. All right, second note about the directional derivative, this only works if u is a unit vector. All right, so again, with a slope, we're going to go 1 unit in the u direction and then figure out how much z is changing in that direction. All right, last thing about the directional derivative before we actually calculate one, this directional derivative is a scalar quantity. It's a dot product, so it's a number. All right, so we have a function, f of xy is equal to sine x times cosine y. And we're to find the directional derivative at the point pi over 3 comma pi over 3 in the direction of the vector for -3. So we're going to have to find the gradient of f. We know how to do that from the last video. and we're going to dot it with vector u. Now remember that u has to be a unit vector, and they gave us the vector 4, -3. It's not a unit vector. So the first thing I'm going to do is convert that vector v into a unit vector. All right, so I'm going to do this off to the side over here. All right, so our unit vector is going to have to be the vector v divided by its own magnitude. All right, so we're going to take our vector. I'm going to switch over to bracket notation. 4, -3, and I'm going to divide that by its own magnitude. So it's going to be 4 squared, 16, and -3 squared is 9. And that's a beautiful magnitude, all right, because it's the square root of 25, so 5. So we're going to be dividing each component by 5 to get our unit vector. Okay, so that's the vector that's pointing in the same direction as v. It's just got 1 unit long. All right, so we're going to dot that vector, looking down at our red box, we're going to dot that vector with the gradient at our point. So let's calculate the gradient. All right, so our gradient, we're going to take the partial derivative of sine x times cosine y with respect to x. So when I'm taking the derivative of my function with respect to x, the cosine y is just a constant. So I take the derivative of sine x, which is cosine x. But the cosine y was just a constant, so we're just going to leave that as cosine y. All right, gradient in the second component, we take the derivative with respect to y. So back up to my blue bracket. Now the sine x is the constant, and derivative of cosine is negative sine. So we're going to have times negative sine y. All right, so let me put that negative out front so it's easier to look at. So we've got our gradient function, cosine x, cosine y, comma, negative sine x, sine y. Okay, so that's our gradient for every single point on the whole surface. We're only interested in what the gradient is doing at the point where x is pi over 3 and y is pi over 3. So let's actually plug that in to our gradient function. So we're going to plug in pi over 3, comma, pi over 3. And I get a whole bunch of sines and cosines of pi over 3. So cosine pi over 3, cosine, they're both pi over 3. And then negative sine pi over 3, sine pi over 3. All right, unit circle time if you don't have that memorized. Cosine of pi over 3 is 1/2. So I'm going to have 1/2, comma, no, not comma, times 1/2. Then I've got negative sine of root pi over 3 is root 3 over 2. Sine of pi over 3 is root 3 over 2. And so I get 1/2 times 1/2 is 1/4. And root 3 times root 3 is 3. So I've got negative 3 over 4. All right, so that's my gradient at the point that we're interested in. And I have my unit vector. So our formula says that the directional derivative in the direction of u of our function f is going to be our gradient vector dotted with our unit vector, which we found was 4/5, negative 3/5. Okay, so a lot of fraction multiplication, right? I've got 1/4 times 4/5, multiply component-wise, and then add negative 3/4 times negative 3/5. All right, I could cancel out those 4s, but I see a common denominator coming, so I'm going to leave it. Multiply across the top, I get 4 over 20 plus 9 over 20. And then I've got the common denominator. I can add them, 13 over 20. Okay, so like I said, directional derivatives are going to be scalars. We got 13 over 20. Let's go over to GeoGebra and think about what this actually means. All right, so here's our surface, sine x times cosine y. And we were given the point pi over 3 comma pi over 3. So let me turn that point on. So this is the point that's down in the xy plane. You can see that's in the xy plane. It's not on the surface. Okay, so the directional derivative does go up to the surface. We've got that point on the surface that's right above that point that was given to us. Okay. And what it does, it takes that vector u that we were given, which is an R2, so that's down in the xy plane with the point A, and it says, what is the function doing? What is the z coordinate doing in that direction? So it's going to look at the tangent line in that direction, all right? And it's going to say, if I go 1 unit in the direction of u, okay, so I'm going to put that vector there. So from B, it's going to travel 1 unit in the direction of u. How far does it have to change z coordinates to stay on that tangent line? Okay, and that is that distance right there. So at that point along the tangent line, it's kind of a slope, right? If we go 1 tick mark in the u direction, how much do we have to change our z coordinate to stay on that tangent line? And we have to change it by a y coordinate of 13/20 z tick marks. And that's what the directional derivative is telling us.